In today's session, we're going to discuss roots and radicals, and we're going to start by talking about expressing a radical in simplest radical form. Alright, and when we're talking about a radical, we're just saying any term that's being raised or is under some type of root. So square root, third root, fourth root, cube root. That's what we mean by radical. Okay. Now, before we actually get into looking at some problems and trying to put them in simplest radical form, I think it may be useful if we just real quick discuss a listing of perfect squares and perfect cubes. Alright, so let's just real quick go through a listing first for perfect squares. 1 squared is 1, 2 squared is 4, 3 squared 9, so on and so forth, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196, and 225. Alright, so 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6, 7, 8, 9, 10 squared, 11, 12, 13, 14, 15 squared. Now I'll skip 16, 17, 18, 19, and then write, 20 squared here. Alright, because these are the ones you'll see most common. Alright, these here. Alright, so what you'll be doing is looking for numbers that fall in this listing as perfect squares. Now for the cubes, our perfect cubes, we won't go as long with our listing. We'll just go to 10. So 1 cube, 2 cube, 3 cube, 4 cube, 5 cubed, 6 cubed, 7 cubed, 8 cubed, 9 cubed, and 10 cubed. Alright, this listing. So now that we have our listing, this is a listing of perfect cubes from 1 to 10, list of perfect squares from 1 to 15, then skips to 20. Alright, so you want to do your best to make use of these two lists. Now let's just say we have square root of 8. Alright, when you're having the square root or cube root of whatever the case may be of some number, what you want to do is you want to find the highest number that fits with that root. Okay, so we're talking square root. Okay, so I want to find factors of 8, and square root, when we talk square root is the inverse of squaring. Okay, so if you take the square root, you want to use this list. If you take the cube root, you want to use this list, because squaring something is the inverse of taking the square root of it. Cubing something is the inverse of taking the cube root of it. Okay, so we have the square root of 8, so that means I want to look at my list of perfect squares over here, and I want to find the biggest factor for 8, if at all possible, that fits on this list. Okay, well I know 8 fits in here, so it'd have to be something, one of these two factors. Well, 1 doesn't change anything, so really we throw 1 out of the equation. Okay, so we look at 4. Is 4 a factor? Yes, it is. So what we say is 8 is like saying square root of 4 times the square root of 2. Okay, so square root of 8 is like saying square root of 4 square root of 2, and we know 4 is a perfect square because there it is on our list. So we take the square root of 4, which is 2, square root of 2. 2 is not a perfect square. It is not on our list. So we don't break it down any further, and we just leave it as square root of 2. So if I took the square root of 8 and wrote it in simplest radical form, my answer would be 2 square root of 2. Alright, let's look at another one. Let's say we have, let's say, square root of 45. Okay. Now, we're looking at 45 and its square root. So again, I go to this list here, my perfect square list, and 45 fits right in here. So I would be looking at any of these to be factors of 45. Well, I know 36 doesn't go into 45, 25 doesn't go into 45, 16 doesn't go into 45, but this 9 does. So 9 is my biggest factor in my perfect square list that goes into 45. So I say 45 is like saying the square root of 9 times the square root of 5. 9 times 5 is 45. Well, I know 9 to be a perfect square because there it is in our list. So the square root of 9 would be 3, and 5 is not a perfect square. It's not in our list. So we just leave it under the radical sign. Okay? And so our answer is 3 square root of 5. So square root of 5 put in simplest radical form would be 3 square root of 5. Okay? Let's say now we have cube root of 24. It's not square root anymore. You have to pay attention. Right here there's a 3. If there's no number there, then we assume square root, like this one and this one. But once you put a number there, that changes it. So if that's a 3, then you go to your perfect cube list because there's your 3. Okay? Alright. So we're looking at our perfect cube list because cubing something is the opposite or inverse of taking the cube root of that. Alright, so 24, we say 24 would fit in between 8 and 27 on our list. So we're asking ourselves, would any of these, and again we throw 1 out of the mix because dividing anything by 1 doesn't change anything. So we look at 8, and we see that 8 does go into 24. Alright, so the cube root of 24 is like saying the cube root of 8 times the cube root of 3, because 8 times 3 is 24. So the cube root of 8 times the cube root of 3 is the cube root of 24. And we said that 8 is a perfect cube. Here it is right here on our perfect cube list. And cube root of 8 is 2, because 2 times 2 is 4 times a third 2 is 8. So perfect cube of 8 is 2. 3 doesn't have is not a perfect cube, so we leave it. There you go. So your answer is 2 cube root 3. Alright, if you simplify this, that would be your answer. Let's look at another cube root. Let's say we have 54. Okay. Alright, well 54 fits in between those. We check, see what our biggest factor is. Does 27 go into 54? Yes, it does. Alright, so I know it. Cube root of 27, cube root of 2. 27 times 2 is 54. Okay, 27 is a perfect cube. There it is on our perfect cube list. So perfect cube, cube root of 27 is 3. Okay, 2 is not a perfect cube, so it stays under the radical. So there's your answer in simplest radical form. Alright. Here, let's try some other ones. let's go with this will be a good one. Let's say 3 square root of 80, and we want to put it in simplest radical form. Alright, 3 square root of 80 in simplest radical form. Alright, this is a square root sign. So now we come back to our perfect squares list. Okay. Alright. So we have our perfect squares list, right? Right here, perfect square list. So 80, we don't worry about the 3 that's outside, it's not under the radical. We're trying to break down what's under the radical, and in this case the radical is a square root. Alright, so we find where 80 would be. 80 would be in between here. So I'm checking these for factors, starting with 64, working my way down, or working my way up the list, but down in value. 64 doesn't go into 80, 49 doesn't go into 80, 36 doesn't go into 80, 25 doesn't go into 80. Let's see, what about 16? 16 going to 80? Yes, it does. Alright, so 16 would be the biggest factor we found on our list that goes into 80. So 80 is like saying the square root of 16 times the square root of 5. Alright, because 16 times 5 is 80. Now we know square root of 16 to be 4, and the square root of 5 is not a perfect square, so it stays in the radical, right? But this right here is just for the square root of 80. We cannot forget about the 3. So the 3 is still out here and gets multiplied with the 4 I got from the square root of 16. So 3 times 4 now gives me a 12 square root of 5. So this ends up being the answer in simplest radical form. Alright, let's look at another one. Let's see. Let's see if we can find us another good one. Okay, here's one. Let's go with 2 cube root of 81. Alright, 2. Now this is not a cube on the 2. This is showing me a cube root for this radical. Alright, so really this is like saying 2 times the cube root of 81. That's what we're really doing. Okay, same here. This was like saying 3 times the square root of 80. 2 times the cube root of 81. So we want to focus on the cube root of 81. Check our list. Alright, so now we're talking cube root, right, because of the 3 here and here. So now we're looking at this list. So we're saying we have 81, which fits in between there. So I'm checking these going this way. Alright, 64 doesn't go into 81. What about 27? 27 goes into 81. What is that? 3 times. Okay, so the cube root of 27 times the cube root of 3. 27 times 3 would give me 81. So cube root of 27 times the cube root of 3 would give me a cube root of 81. Alright, we know the cube root of 27 to be 3. 3 is not a perfect cube, so stays under the radical. And now this that you see here, 3 cube root of 3, is just for the cube root of 81 part, but you still have this 2 out here, so this 2 gets multiplied by that. Alright, and so when you do that multiplication, what you end up with is 2 times 3, which is 6. Alright, 6 cube root 3. Okay, alright, So that's taking a radical and putting it in simplest radical form. Okay. Alright. Now let's discuss. Let's erase this first of all. Okay, now we want to talk about rationalizing the denominator. Alright, rationalizing denominator. Alright, in order to simplify a radical. Okay. Now what we're talking about here is basically a situation in which you have a radical in the denominator of a fraction. We do not like that. Alright. And we said that square root is the same as saying something squared, or not the same, but is linked with squaring something. So to undo square root, you want to square something. If you're trying to undo the squaring of something, you take the square root of it. Alright. So these two operations, square root and square, are inverses of one another. And in the same manner, the cube root of a number, alright, the square root of a number is the inverse of squaring a number. The cube root of a number is the inverse. I'm messing up now. Is the inverse of cubing a number. Alright. So these two cancel each other. Okay, and really they go back and forth. So that'd be a better way to denote it. Okay. Now, if you're presented with a situation in which you have something like the square root of 2/3, okay, so this whole fraction is under the square root sign. Alright, this really is like saying the square root of 2 over the square root of 3. Alright, I just took the numerator and the denominator and put them under the common sign, which is the square root sign, the common radical. Now, rationalizing the denominator is about us trying to simplify a radical by getting rid of the radical in the denominator. Okay? Now, we don't like radicals in the denominator. In this case, we have a square root in the denominator. And we said to undo square root, you have to square something. Okay, so if I want to undo the square root of 3, then all I need to do is square it. And squaring just means to multiply that thing by itself, because now I have two of them, which is like squaring them. Alright, now whatever I do in the denominator, I must do the same in the numerator. So when I go and work this out, square root of 2 times the square root of 3 up top gives me square root of 6. In the bottom, square root of 3 times the square root of 3 gives me the square root of 9. Alright, now if you notice, 9 is a perfect square. Square root of 9 equals 3. Now we don't have a radical in the denominator anymore. Now 6 is not a perfect square, okay, and so we leave it as it is, square root of 6. We don't worry about the radicals in the numerator. We just got to make sure that we don't have them in the denominator, and in this case we don't. Alright, look at another problem. Let's say we have square root of 5 over square root of 8. Again, we have a square root or radical in the denominator, in this case a square root. So what we want to do is take this square root of 5 over the square root of 8 and multiply by this again so that we get the square here. Alright, if we take this and multiply it by itself, that's like squaring it. Okay, well, whatever we do in the denominator, we also have to do the same thing in the numerator. And what do we end up with? In the numerator, we end up with the square root of 40. And in the denominator, we end up with square root of 64. Alright, now In the numerator, we know 40 is like saying 4 times 10. The reason why I chose 4 is because 4 is a perfect square. Alright? So if I took the square root of 4, because it'd be the square root of 4 times the square root of 10, alright, to give me 40 in the numerator. So if I took the square root of 4, here, let me just go ahead and write it out. Alright, so my square root of 40 is like saying square root of 4 times square root of 10. And the square root of 64, we already know, is 8, so I don't have a radical in the denominator anymore, but I still can simplify the numerator a little bit more. Square root of 4 is 2. Alright, 10 cannot be broken down by a perfect square, so it stays under the radical. And you have your 8 in the denominator. Well, we look and see this 2 and this 8, they're not under the radical. Okay, so we can look at reducing this like you would reduce a regular fraction. Alright, 2 over 8 reduces down to 1/4. Alright, but because we have this radical 10 in the numerator, we don't have to write the 1. We can just write the radical 10 because it's understood that there's a 1 out here in front of it. Alright, here, let me write this. I write this better down here. Alright, so it's understood that there's a 1 there, but you don't write it. You just write the radical 10 over the 4. Alright, because 2 over 8 reduces to 1/4, but because there's a radical 10 up here, you would not write this 1 right here. So it'd just be radical 10 over 4. But you understand that there is a 1 right there from the 1/4 you get. Okay? So again, the answer would just look like this. Alright. Let's see. Let's do one that has a cube now. Let's go with cube root of 5 over cube root of 16. Okay, now we have a radical in the denominator. We say we don't like that. In this case, it's a cube root. So now instead of squaring, I want to cube the denominator to get rid of it. Well, if I notice, 16 is actually a perfect square. So 16 is like saying I've already taken the number 4 and multiplied it by itself twice. So now to cube it, let me do it a third time. Okay, and whatever I do in the denominator, I must do in the numerator. Alright, so if I multiply 16 times 4, I get a perfect cube. If you go back to the perfect cube list I gave you on the previous screen, you would see that 6 times 4 gives me cube root of 64, which is a perfect cube. Alright, and up top in the numerator, 5 times a 4 gives me a 20. Okay, so cube root of 64, now I have a perfect cube, which gives me, what is that, 4, right? Alright, cube root of 64 is 4, and in the numerator 20, it cannot be broken down by any perfect cubes because the only option I could use would be 8, and 8 doesn't go into 20 evenly, so it would stay under the cube root. So this is what I would have: cube root of 20 over 4. Alright, let's look at another one. Let's look at, let's say cube root of 5 over cube root of 9. Now, I have a radical in the denominator, in this case a cube root, so I need to get a perfect cube. So I could take this and multiply it by itself 3 times. Okay, alright, show you this 2 ways. I could do this. Alright, I could multiply this, since it's a cube root that I'm looking for. To undo cube root, I cube something, so I could write it 3 times, which would cancel each other out, just like I'm showing you here. Cube root cancels cubing, so it would cancel out and just give me a 9 in the denominator, and I'd multiply the top, what, 45. That would be like saying 5 times the 9 times another 9. Okay, so you'd have this 5 times this 9 times this 9, which would give me the cube root of 405. Alright, that would be one way to go. Okay, and then you see if you could break the 405 down. Alright, so that's one way to go. But another way to deal with the same problem is to just say, okay, what can I multiply this 9 by, if I can, to get to another perfect cube, one of the numbers that's on my perfect cube list. And I know 9 goes into 27, and 27 is on my perfect cube list. So this problem could have also been handled by just saying 9 times cube root of 3, because 9 times 3 is going to give me 27. Alright, whatever I do in the denominator, I do in the numerator. So here I end up getting, what is this, cube root of 15 up here. Alright, and here I end up with what is that, 27 cube root of 27. Okay, so now 27 is a perfect cube. I take the cube root of 27, I get a 3. Okay, and up top I have the cube root of 15. 15 cannot be broken down any further, so it stays cube root of 15. Alright, so I have cube root of 15 over 3 for an answer. And up here, what I should have, let's see, 27, oh wait, 3, yeah, 405 divided by 3 equals 135. Let's see, is that right? 3. That's not what I want. Let's see. 3. 15. 405 divided by 15 was 27. There we go. Okay. Here we go. So if we would have continued to do the one up here, I would have found that 405 would be like saying the cube root of 27 times the cube root of 15 all over my 9, and the cube root of 27 happens to be a 3, and you're left with cube root of 15, and it's over 9, and the 3 cancels with the 9 and leaves a 3 down here. So just like we said, you end up here with cube root of 15 over 3, which is the same thing you got down here. Alright, so just showing you 2 different ways that you could have attacked that problem. Okay, let's try 3 square root of 2 over 5 square root of 3. Have a radical in the denominator, want to get rid of it, so I multiply. Since a square root, I try to square it, so I write the same thing twice. That's squaring it. Write the same thing in the numerator. Okay, so now I end up with up top 15, because the 3 times the 5 is 15, and then the square root of 2 times the square root of 3. You cannot multiply the 3 with anything under the radical, and the 5. 3 and the 5 are outside of the radical, so they get multiplied. The 2 and the 3 are under the square root, so that's what gets multiplied. Okay, same down here. The 5 and the 5 are outside, so that gives me a 25. The 3 and the 3 are inside, that gives me a 9. Alright, and so that's 15 square root of 6 over 25 times square root of 9, we know is 3. Okay, now 3 goes into 15, and it leaves me 5 left over. 5 goes into 25 and leaves me 5 left over. So in the end, I really don't have anything up top but the square root of 6, and in the denominator in the bottom I have a 5. Okay, so my answer, square root of 6 over 5. Alright, so there you have it. That's rationalizing the denominator. Any questions, please feel free to contact me. At this time, we will now conclude this session.